All right, good morning everyone, and thank you for attending our presentation and the conference. So, artificial intelligence is everywhere. From self-driving cars to autonomous drones to collaborative robots, we're adding AI to our products, our services, and our world. According to the McKinsey Global Institute, AI is expected to generate $13 trillion in real economic value by 2030. And now this is a 16% increase from our current global GDP. In addition, by 2030, AI is expected to automate approximately 600 million jobs, and that's roughly 22% of all jobs that currently exist today, likely gone within the next decade. Fortunately, though, they're also predicting 700 million new jobs will be created by 2030, and many of these jobs are going to be jobs that require AI tech skills. So ultimately, this is going to be a tremendous disruption to our labor economy in less than a decade if these predictions are correct. However, most software developers and IT professionals have not yet added these new AI tools to their professional developer toolkits. So they don't have the skills necessary to meet the demands of an AI-first economy. As a result, they don't know what is currently possible with modern artificial intelligence. They don't know how to add these AI capabilities to their products and services. And they don't know how to tell if an AI solution is going to provide real economic value to their customers. Essentially, they're in the dark during the single most important technology revolution of our lifetimes, at least. A revolution that's literally happening right before our very eyes. All right, before we begin, I think I should introduce myself so you know who I am, where I come from, and why I'm interested in this topic. So my name is Matthew Renze. I'm a data science consultant, author, and public speaker with over 20 years plus industry experience. I'm the owner of Renze Consulting, a data science consulting firm that's taught over 400,000 software developers and IT professionals. I'm also the president of Renze Global, which is a nonprofit organization dedicated to improving access to technology education for underrepresented individuals. And I'm working on my master's degree in artificial intelligence right now through Johns Hopkins University, but I already have degrees in computer science and philosophy with a minor in economics, in addition to a data science specialization through Johns Hopkins. And I'm also a Microsoft MVP in AI, an ASP Insider, and I'm an author for Pluralsight, Skillshare, and Udemy. And just for fun, I have presented on every continent in the world, including Antarctica. But enough about me, let's talk about some AI. So the purpose of this presentation is to survey the most popular modern data-driven AI tools. We're talking about easy-to-use, off-the-shelf machine learning models that you can use today to automate a variety of operations in your products and services, many of which are currently better than humans at performing the equivalent task. As an overview, first, we're going to look at AI tools for working with tables of data, structured tabular data. Next, we'll look at AI tools for working with text, then AI for audio, AI for images, AI for video, and then we'll learn how to wire these models together to create modular AI applications. And finally, we'll end with learning about cyber-physical systems, things like robots and self-driving cars, and how they build these systems. All right, we're going to start with the simplest tools, and we're going to work our way down to the more complex, and in my opinion, the more interesting tools later. So some of you will have likely seen some of these tools way at the top here through different videos or at other conferences. And these are the most basic tools that we're going to cover in the first half of the presentation. However, many of the tools in the second half of the presentation are going to seem like total magic. But I assure you, everything that you see today is 100% real. None of this is fake. These are all models that you can either use right now or are coming down the pipeline very soon. So if you're struggling to stay engaged for the early part of the presentation, just bear with me. Things will get way more interesting as we get into the more advanced topics. And I'd like you to think of this presentation like a giant buffet of AI tools. We're going to be sampling lots of different flavors of AI today. However, there's just too many types of AI for us to eat them all in one seating. So we just want to take really tiny bites of each of these topics today. If you find something that you like, you can always dig in later. But we need to move pretty fast to cover as much ground as we're going to cover. All right, so we have a lot to cover, so let's get started. But before we get into the tools, I want to make sure that we're all on the same page about what artificial intelligence is. So we need to answer the question, what is modern data-driven AI? And to answer this question, we need to start with AI itself. So artificial intelligence is a subfield of computer science that attempts to create machines that act rationally in response to their environment. An AI is any machine that perceives its environment and chooses actions that maximize the expected likelihood of achieving a goal of some kind. Essentially, it's just a machine that takes data as input and produces the best possible output given what it currently knows. Some examples of AI include computers that can play chess, robots that can vacuum your floor, non-player characters in video games, and the navigation software on your smartphone. Essentially, any computer algorithm that replicates some aspect of human intelligence or natural intelligence is essentially a form of artificial intelligence. Now, all modern data-driven AI, or most modern data-driven AI, is all based on machine learning. So what is this machine learning stuff? Well, machine learning is a subfield of artificial intelligence that's based on data and statistics. It involves machines learning how to solve problems without being explicitly programmed to do so. So we're not typing if this, then that. It's learning how to do so by detecting statistical patterns in data. Essentially, with machine learning, we use existing data and a training algorithm to learn a model of the data. Then we can feed new data into that model that it's never seen before, and the model will make a prediction about this new data. Now, a machine learning model is essentially just a function. It's simply a mapping from an input to an output of some kind. And in the most basic case with machine learning, we're essentially using a model to take data as input, and then that model is producing some kind of prediction or decision as output. And this is a very important point to make, because every example that we're going to see here today is essentially just some kind of function. We're mapping some kind of input to some kind of output. And you'll see this pattern over and over and over again in both machine learning and artificial intelligence. So in terms of this mapping between inputs and outputs, there are two main types of input-output mappings that are sets of tasks of these input-output mappings that we can perform with machine learning. We can either perform data analysis or we can perform data synthesis. So analysis is where we take complex high-dimensional data as input and then reduce it to lower-dimensional, more abstract data as output. For example, converting text, audio, or video into a single number or label of some kind. Synthesis, on the other hand, is where we take lower-dimensional, more abstract data as input and then produce higher-dimensional, more complex data as its output. For example, converting simple text into more complex audio or video, speaking that text out loud. Throughout this presentation, we're going to group all of our models first by the type of data that they involve, and then second as either an analysis task in blue or a synthesis task in green. And this is going to help you to build a mental model of the entire landscape of artificial intelligence and the various tasks that we can perform with modern data-driven AI. And finally, there are three main types of machine learning models. We have pre-trained models, augmented models, and custom models. And now, pre-trained models are essentially off-the-shelf solutions. They've been previously trained by a third party like Microsoft, Google, or Amazon to perform a general task, and then they're ready to use with little to no additional effort from you as a developer. For example, Microsoft has a pre-trained vision service that allows you to detect people's faces in an image. Simply just make a REST API call, and you get an answer back. Now, on the far other end of the spectrum, we have these custom do-it-yourself models, where you have to provide the training data, the compute power, and the expertise in order to create a model that will perform a specific task for you or your business. For example, if you wanted to predict customer revenue based on your customer's financial history, you would need to use your own company's data, you'd need to use your own compute power, and your own expertise to create this model from scratch. Augmented models are somewhere in between. So the models are pre-trained by a third party like Microsoft, Amazon, or Google, and then you transfer the learning from your more specific task to that, from the more general task to your more specific task. For example, if you wanted to detect your company's logo in images, you could use a pre-trained vision model and then apply transfer learning by giving it a few examples of your company's logo, and then it's going to essentially detect just your company's logo in the images going forward. Now, I've ordered these three types of models by their level of difficulty, complexity, and cost. So I always recommend that you start with the easiest pre-trained models first and only work your way to the more complex custom models if and when necessary. All right, so now let's get into the actual tasks that we can use these tools for. So first, we're going to look at learn how to use AI tools to work with tables of data. So tables are how we organize structured data about our world. They can contain data about scientific observations, business transactions, physical entities, and more. As a result, they're the most common form of structured data that we encounter in information technology. Tabular data are simply data stored in rows and columns of a table. Now, on the rows, we typically have the individual observations, transactions, or entities, and on the columns, we typically have the individual variables, properties, or attributes. And there are two main types of data that we can store in these tabular data types, both categorical and numerical data. So categorical data represent named qualities of things. For example, true or false, various colors, or t-shirt sizes. Whereas numerical data represent quantities of things. For example, integers, decimals, floating point numbers, and so on. And there's a variety of data analysis tools that we have available to us for working with tabular data. For example, classification, regression, recommendation, and more. So let's just take a look at classification, which I think is the easiest of these to understand. So classification allows us to assign a row of data to 2 or more categories. Essentially, it answers what kind of data is in this row in the table, or how would we classify this row of data? So for example, you can use a customer's data to approve or reject a credit card application. We provide the model with the customer's financial data as input, and then the model produces a label indicating the likelihood of repaying the credit card on time and a confidence score in that prediction as its output. Classification is useful for tasks like automating the approval or rejection of bank loans, detecting potential fraud during credit card transactions, and predicting customers who are about to leave us for their competitors, which we call customer churn. Now, beyond classification, we have a variety of other data analysis tools available for tabular data. For example, regression, where we use existing rows of data to predict numeric values for those new rows. Recommendation, where we suggest data that are similar in some way to other data, like products, services, or movies that we're recommending. Clustering, where we group rows of data together based on similarities to one another. Association, where we determine the strength of the relationship between connected rows of data. And anomaly detection, where we determine which data are atypical or abnormal compared to the rest of the data. Now, in addition to the data analysis tools that we've just seen, there's also a variety of data synthesis tools for tabular data. For example, data imputation, data generation, and data transformation. So we're going to take a look at imputation. Now, imputation allows us to predict which value of predict values of missing categorical or numerical data. Essentially, it answers the question, what data should go in this missing spot? Or, how would I fill in this data based on all the other data around it? Essentially, it's doing this in a statistically sensible way. So, for example, imagine we've got a table of weather data, and we have a bunch of missing sensor data readings from various days. Now, if we would provide the model with this input table of data containing the missing values, and then the model's going to produce a complete table with those missing values filled in with sensible alternative values, or replacement values. Now, imputation is useful for tasks such as creating data visualizations that require complete data, performing aggregate data analysis that requires summing values together, where you need all of the values, and creating machine learning data sets that require complete data in order to train the model. Now, beyond data imputation, we've also got a few other types of data synthesis tools. For example, data generation, which allows us to synthesize entire tables of data from scratch while preserving the statistical characteristics of a source table of data. And data transformation, which allows us to convert data from one format into a second format simply by giving it a few examples of what the transformation should look like. And so as we can see, there's a variety of tools now available to software developers for working with tabular data, and these include both tools for data analysis as well as data synthesis. So next, we're going to learn how to use AI tools for working with text. Now, text is how we communicate information to one another via written language. It's the primary type of data that we encounter in books, articles, and emails, and as a result, it's one of the most valuable forms of unstructured data that exist in information technology. Textual data are data that are represented as a body of text, like this example passage from Shakespeare. We typically store textual data as an array of characters of an arbitrary length. Each letter, number, and symbol are represented as a binary value within this array. And there are a variety of AI tools that we can use to perform analysis on text in this format, which we also call natural language processing, or NLP. These text analysis tools include text classification, sentiment analysis, entity recognition, and more. So we'll take a look at the simplest of these, which is text classification. Text classification allows us to assign a body of text to 2 or more categories. In essence, it answers the question, what kind of text is this, or how should we assign this text to a category? For example, we could classify inbound emails by the department that typically handles them. We provide the model with the text contained in an email as input, and then the model produces a prediction of which department the email should be routed to as its output. Text classification is useful for tasks such as organizing legal documents based on the type of case that they involve, categorizing support tickets by the type of issue, and classifying spam email as either spam or not spam. But beyond text classification, we also have a variety of other text analysis tools. For example, sentiment analysis, which allows us to determine if a body of text has either positive or negative emotional sentiment. Entity recognition, which allows us to identify specific persons, places, or things in a body of text beyond simple word matching. Tone analysis, which is like sentiment analysis, but for different types of emotion and tone in emails or in text. Language detection, which allows us to determine the language of a written body of text. And syntax analysis, which organizes words into a hierarchical tree representing each word, their part of speech, and their syntactical relationship. Now, in addition to the text analysis tools, there's also a variety of text synthesis tools. These include tools like text completion, text generation, language translation, and more. So we'll take a look at text completion. Text completion allows us to predict missing words or upcoming words. In essence, it answers the question, what word is missing here, or what word is most likely to come next? For example, we can use text completion to predict what words a user is likely to type next into their smartphone. We provide the model with the text of an incomplete sentence as input, and then the model produces the most likely text and a confidence score as output. Text completion is useful for tasks such as auto-completing sentences while you're typing, correcting transcription errors while transcribing from videos, or verifying sentence syntax by checking the probability of occurrence of each word in a sentence to see whether that word makes sense there or not. Now, beyond text completion, there's also a variety of other text synthesis tools, including text generation, which allows us to generate an entire body of text based on a simple text prompt. Language translation, which allows us to convert from one language to another language. Text summarization, which reduces a very large body of text down into a little TDLR summary of, or synopsis of the text. Language transliteration, which can convert words from one alphabet into words that are pronounceable in a second alphabet. And program synthesis, which converts visual descriptions in pseudocode into actual source code that can be run by a computer. Has anyone used like either Codex or like GitHub's? Okay. And did anyone read the new article about Amazon's competitor to that just came out? It's actually got peer reviewing built into it as well, where it will do like pair programming with you, it looks like. So that's going to be pretty impressive. We'll see how well that works, because I know from my own experience that code synthesis works extremely well in anything you could copy and paste from GitHub, but when you get into more complex domains, it often fails kind of miserably. So as we can see, there's a variety of AI tools available to developers for working with text, and these include both tools for text analysis as well as text synthesis. All right, so who's interested in seeing a demo of how easy this stuff really is? Show of hands. Okay, yep, that's exactly where I'd be at in this presentation. I'm seeing all this stuff, but is this actually easy to use? So in this demo, we'll perform sentiment analysis on a body of text. We're going to provide the model with a series of 3 short text documents as input, and then the model will return a sentiment class for each document and a confidence score as its output. We're going to perform this demo using Python and a cognitive services in Microsoft Azure. However, this process is very similar regardless of the programming language or regardless of which cloud API provider you're working with, or cloud AI provider. So, and that includes Google, Amazon, and many others using either client SDKs or pure REST API calls, which we'll see both of those here coming up. In addition, this process is very similar regardless of the type of data that you're working with as inputs and outputs. However, instead of text, you'd be working with like audio, images, or video as your inputs, and various labels or text as output. And normally I do live code demos. However, cloud-based demos across the world on rapidly changing APIs don't always work out so well. So I'm just going to be walking through each line of code here in this document and explaining it as we go. And it should be pretty simple and easy for us to follow along. In fact, it's probably good that I changed this because Microsoft just announced a breaking change in the second demo that I'm going to be showing you here this week that I would have had to update the demo for in order to accommodate. All right, so first, we import the client SDK libraries for our Azure Key credentials and our text analytics client. Next, we set the endpoint URL to our API's endpoint. Then we set our Azure subscription key. Next, we create Azure credentials with our subscription key. Then we create a text analytics client with our endpoint URL and the credentials that we just created. Then we scroll down. Now we're going to create 3 text documents. Hello world, I love you and I hate you. Then we'll analyze the sentiment of our documents by sending them to our cloud API via this client SDK call. And finally, we'll loop through the results and print the results of our sentiment analysis. And literally that's it. In 10 lines of actual code, we've essentially implemented sentiment analysis in our program or our tool. And that's all it really takes. It's surprisingly easy to do this nowadays. So let's take a look at the results. So as we can see, our Hello World document has a neutral sentiment with a confidence score of 97%. The I Love You document has a positive sentiment with a confidence of 100%. And the I Hate You document has a negative sentiment with a confidence of 100%. And I mean, that's pretty simple and easy to understand, even for someone who doesn't know anything about AI or machine learning, right? All right, and here's that same demo using Google's Cloud AI services. As you can see, it's pretty much all the same thing. We essentially set up our environment, we create some documents, we create a client, we then send that document through the client, and then we print the results. And the exact same thing again using Amazon's AWS AI web services. Exact same kind of process. Ridiculously simple to do this kind of stuff nowadays. It doesn't take a PhD and a team of data scientists to add AI to your products and services. All right, so third, we're going to learn how to use AI tools to work with audio. So audio is how we hear the world and speak to one another. And as a result, audio is essential to our understanding of the world around us. Audio data are typically stored as a one-dimensional array of numeric values. Each value represents a sample of the amplitude of a sound wave recorded at a specific time. And then these samples are ordered across time to create a temporal representation of the recorded sounds. For monaural sound recordings, we just have a single audio channel and thus a single array of values. For stereo data, we have two channels, that is a left channel and a right channel. As a result, stereo audio data typically contain two channels, one for each audio channel, then synchronized across time. And there are a variety of AI tools that we can use for audio analysis, and these include sound classification, speaker recognition, speech recognition, and more. So let's take a look at sound classification. Now, sound classification allows us to assign a sound to two or more labeled categories. Essentially, it answers the question, what kind of sound is this? For example, we can use sound classification to determine which type of animal produces a specific vocalization or noise. We provide the model with the following audio sample as input. I'm going to play a sound, hopefully it's not too loud. And then, just like our ears can predict what kind of thing that is, the model is going to produce an answer as to what it thinks that sound came from and a confidence score for that prediction as its output. Sound classification is useful for things like detecting gunshots in audio surveillance systems, predicting mechanical failure from acoustical anomalies, and identifying species of wildlife for wildlife conservation. But beyond sound classification, we have a variety of other audio analysis tools. For example, speaker recognition, which allows us to determine who is speaking in a sound recording. Speech recognition, which allows us to convert spoken dialogue into written text. Sound detection, which identifies the beginning and end of each sound event in a noisy environment. Sound localization, which can locate the source of a sound in either a 2- or 3-dimensional space. And song recognition, which identifies a song based on a short audio snippet. I'm sure some of you have used like Shazam or something to figure out what song's playing on the radio. Yep. But now, in addition to these audio analysis tools, there's also a variety of audio synthesis tools. These include speech synthesis, voice synthesis, speech translation, and more. So let's look at the most basic, which is speech synthesis, also known as text-to-speech. So speech synthesis allows a computer to communicate to us using spoken words. Essentially, it allows a computer to speak aloud using an artificial human voice. For example, we can use speech synthesis to read text out loud to us. We provide the model with the following text as input, and then the model is going to produce the following audio as output.
Hi, my name is Matthew Renze.
Now, obviously, it's not the sound of my voice saying that, and you can tell it's not entirely human, but it's getting better and better each year to the point where it's going to be very soon we won't be able to distinguish whether we're talking to a human on the other end of the phone or a machine. In fact, if those of you that have seen Google's demo where they essentially had a voice assistant placing a haircut appointment, the person on the other end had no idea that they were talking to the machine during that demo. It's actually quite impressive. But we also have a speech synthesis being useful for things like detecting responses to requests for hands-free applications, narrating text contained in documents, and for creating more natural user interfaces. But beyond speech synthesis, there's now also a variety of other audio synthesis tools. For example, voice synthesis, which takes a recording of a person's voice like this.
Hi, my name is Matthew Renze.
In addition to text transcript edits like that down there, and it's going to produce new audio output combining my voice with the edits that I just made to that text. Like,
hello, I'm Matthew Renze. I'll be your virtual instructor today.
And once again, you can tell it's not perfect, but that's my voice clearly, and it sounds like I'm saying it. And I should probably update this demo because within 1 year since I originally recorded that, this has gotten significantly better, like to the point where I almost can't even tell that it's not me. Speech translation allows us to translate words spoken in one language like this.
Hi, my name is Matthew Renze.
Into words spoken in a second language like this.
Hola, mi nombre es Matthew Renze.
And my wife and I have little earbuds that actually allow us to do real-time translation so we can have conversations with taxi cab drivers that don't speak English, or and when we're traveling in different countries, if we're interested in listening into conversations while, I don't mean like listening in, but like if we're listening to a presentation, we can actually have the earbuds in and hear what they're actually saying in English. We've also got sound generation, which allows us to add realistic sound effects to silent videos, though there's not a whole lot of practical applications for that. Instrument translation that can take a song performed by one instrument like this, and then recreates it using a second instrument like that. And that leads to music generation, which allows us to compose entirely new songs from scratch, like this 100% fake Frank Sinatra song, Hot Tub Christmas.
It's Christmas time and you know what that means. Oh, it's hot tub time. As I like the tree this year, you'll be in a tub.
I mean, if I didn't know better, I would think Frank Sinatra recorded this song, but it's just synthesized by a computer that understands all of Frank Sinatra's songs and its intonation, and essentially you just create the lyrics for the song and Frank Sinatra sings it to like music of the same classic pop style. All right, so as we can see, there are a variety of modern AI tools available to developers for working with audio, and these include both tools for audio analysis as well as audio synthesis. So fourth, we're going to learn how to use AI tools for working with images. And for me personally, I think this is where things start to get really interesting. So our world is highly visual. We derive most of our information about the world through our eyes. The spaces we navigate, the faces we interact with, and the documents we read are all processed visually. As a result, images are one of the most valuable types of unstructured data that exist for modern AI. An image captures a digital picture of the world. However, if we zoom in, we can see that a digital image is actually composed of a bunch of tiny squares. We call this a raster of pixels, a two-dimensional grid of picture elements. We represent this raster of pixels as either a two-dimensional array or matrix of numeric values, and each numeric value corresponds to the intensity of the light captured at a specific X and Y position of the image sensor. For color images, we typically have separate rasters of pixels for each color channel. As a result, color images will be composed of 3 grids corresponding to red, green, and blue color channels, respectively. Now, similar to audio, we can have both monocular images, that is a flat two-dimensional image, or we can have a stereo image, which allows us to see depth by optical parallax. And depth also helps us to determine the position of objects relative to the observer in space. And there are a variety of AI tools that we can use now for image analysis, and these include image classification, object detection, face recognition, and more. So let's take a look at the simplest, which is image classification. So image classification allows us to assign an image to 2 or more labeled categories. Essentially, it answers the question, what's contained within this image, or what is this thing I'm seeing here? For example, we can use image classification to tag the content of an image. We provide the model with an image as its input, and then the model is going to produce a category label and a confidence score as its output. Image classification is useful for tasks like auto-tagging images on social media posts, detecting visual defects or product defects via visual inspection, or diagnosing medical issues like detecting certain types of skin cancer. But beyond image classification, we have a variety of other image analysis tools. In fact, there are too many to cover all in one short presentation, but I'll briefly cover as many as I can. So we have things like object detection, which allows us to identify the location of various objects within an image. We have face recognition, which allows us to determine who is contained in an image. We have reverse image search, which allows us to find images that are visually similar to a source image. We have image captioning, which generates a text description of what is contained within an image. We have image segmentation, also known as semantic segmentation, which is like object detection, but it applies the object detection to every pixel in the image. So each pixel represents a type of object. Other face analysis tools, which allow us to detect faces, compare faces, detect facial landmarks, determine gender and age, detect facial features, and classify emotions. We have other body analysis tools, which allow us to estimate poses, recognize gestures, count the number of fingers you're holding up, and detect adult or racy content. And other document analysis tools, which allow us to extract printed text, handwritten text, form data, and tables from documents. And this is an area that's growing quite rapidly, especially in the pre-trained AI model space, because we have so many analog forms that need to be digitized. But in addition to the image analysis tools that we've just seen, there's also a variety of image synthesis tools now. And these tools include image completion, image generation, image style transfer, and more. So let's take a look at image completion, which is also known as image in-painting or content-aware fill. So image completion allows us to fill in the missing area of an image with a best guess as to what should likely go there in the missing contents. Essentially, it answers the question, what should go in this missing part of the image? For example, we can use image completion to digitally remove unwanted objects. We provide the model with an image and then a mask containing the object we want removed. Then the model produces a new image with that object digitally removed from the image or the background filled in as its output. Now, this is useful for digitally removing objects from artifacts from images, filling in the missing area outside of the photo's borders, and restoring image quality to old or damaged photos. But beyond image completion, there's a variety of other tools available for image synthesis. For example, image generation, which allows us to generate synthetic images based on a written description. And note, this is not a bird that was found by searching through pictures of bird. This bird was synthesized by the neural network itself. And this technology has really blown up here in just the last year with DALL-E 2 and ImageGen, which vastly outperform even this, so I probably need to update this slide as well. Image style transfer, which allows us to take a source image and an image containing a visual style and then apply that visual style to the source image. Image coloration, which allows us to convert black and white photos into full color images. Image super resolution, which allows us to zoom and enhance the image quality of low resolution images. And I know what you're thinking, oh yeah, this is just the fake stuff they use on CSI to read a license plate. But this technology does exist. It actually works relatively well. You're not gonna be able to pick up the license plate off of the retina of a person's eye reflecting or something. But I mean, this is an actual example. Like I used that image to create that synthesized image, which is quite impressive when you think about it. Depth map estimation, which allows us to create a depth map from a two-dimensional image. Face generation, which allows us to create entirely synthetic human faces given just a few attributes or physical characteristics. And note, this person doesn't exist either. They are completely synthesized. Sketch generation, which can convert a sketch of a person into a synthetic face, which once again, that person clearly doesn't exist as they're being physically changed as we're changing the sketch. Image interpolation, which can fuse the attributes of two images together into a single image. So as we can see, there's a variety of modern AI tools available to developers for working with images, and these include both tools for image analysis as well as image synthesis. All right, so let's see one more demo just to make sure that we understand this general pattern of how to use these tools. So in this demo, we're gonna perform face detection on an image. We're going to upload the image to a cloud-based face detection service via a pure REST API call, and the service will then return the coordinates for a bounding box that contain the face in the image. Once again, we're going to be doing this using a pre-trained model in Microsoft Azure Cognitive Services. It's super simple to set up one of these pre-trained services, so once again, we're just going to skip over that step and go straight into the code. All right, so first, we need to import some libraries for making an HTTP request. Next, we set the endpoint URL to our service endpoint. Then we set our subscription key. Then we set the HTTP headers for our REST API call. Then we set the path to the image on our file system. And let me scroll down. Next, we're going to open the image for binary reading, since it's an image. Then we read the image as an array of bytes. Next, we post the request to the REST API, passing the URL, the headers, and the image data. Then we format the JSON response and just clean up the output a bit for display. And finally, we print the formatted JSON output so that we can see the results. And here are the results. And I've added the HTTP header information up at the top there, or the response header. As we can see, we've got a JSON response body, and it contains a globally unique identifier for the single face that it detected in the image, and it contains a rectangle describing the location of that bounding box around the face. And once again, this is about 10 to 12 lines of actual code to pull this off, most of which actually has to do with creating the HTTP request. But it's really that simple. So with just a few more lines of code, we could draw that bounding box on the image, and this is what it would look like. Once again, as I said, I mean, you really don't need a whole lot of experience with artificial intelligence, data science, or a PhD or any of that stuff in order to use these tools to make your software better or to apply modern data-driven AI to your products and services. All right, so fifth, we're going to learn how to use AI tools to work with video. So the real world isn't composed of static images. Instead, we perceive the world as a rich multimedia experience. When we combine images with audio synced over time, we get video. And video allows us to perceive the world as a continuous and fluid audio-visual experience. Video data are composed of both a visual component and an audio component. The visual component consists of a series of static images that are all stacked over time. And the audio component is synced with the images to produce a temporally coherent audiovisual experience. Video data can either be mono, that is 2D images, or stereo, which is 3D images. And the audio can once again be either one-channel audio, or the single monaural audio, or stereo two-channel audio. And by adding these additional audio and video channels, it improves the accuracy of our models and allows them to perform more complex tasks that couldn't be performed with just a single channel. With video data, keep in mind that we can perform all of the existing tasks that we've seen in the audio and the video, audio and image section. However, the temporally coherent sequence of images and audio combined allows us to perform some new tasks that we couldn't perform with just images or just audio. And this leads to a variety of AI tools that we can use for video analysis, including motion detection, object tracking, action recognition, and more. So let's take a look at motion detection. So motion detection allows us to identify movement in a video over time. Essentially, it answers the question, is there anything moving in this video? So for example, we can determine if anything's moving within a masked region, that little red box of the video. We provide the model with a video and a polygon mask as the detection region as its input, and then the model produces a motion label and a confidence score as its output. Motion detection is useful for tasks like detecting the motion of pedestrians in public spaces, monitoring the movement of wildlife on game preserves, and helping collaborative robots detect humans working within their workspace. Beyond motion detection, there's a variety of other video analysis tools. For example, object tracking, which allows us to track the position, velocity, and acceleration of moving objects in an image. Action recognition, which allows us to identify human activities occurring in a video. Optical flow, which allows us to track the path of moving objects over time. Gait recognition, which allows us to identify a person based on the way they walk. And lip reading, which allows us to convert the movements of lips from spoken text into, or from spoken words into actual text. And this is one of those technologies where the machines are definitely better than the average person at doing this. In fact, the average lip reader, the machines are now better. But in addition to these audio analysis tools that we've just seen, there's also a variety of, video analysis tools. There's also a series of video synthesis tools available. For example, video interpolation, video prediction, video-to-video transfer, and more. So we're going to take a look at video interpolation, which is the ability to predict missing video frames given both previous and subsequent frames. Essentially, it answers the question, what content should go in this missing video frame here? For example, we can create slow motion footage from existing regular speed footage. We provide the model with a slow frame rate video as its input, and then the model is going to produce a high frame rate video as its output, essentially synthesizing each video frame that's missing from this. Now, video interpolation is useful for tasks like upscaling these low frame rate videos to high frame rate videos, restoring old film strips from the old manual crank cameras, and smoothing out multiplexed video security footage where they just store a frame like every second, and you need to synthesize what's happening in between that 1 second frame rate. But beyond video interpolation, there's also a variety of other AI tools for video synthesis, including video prediction, which allows us to provide just a few frames of video and then attempts to predict which next frame or what the next frames would likely look like. Video-to-video transfer, which allows us to use semantically segmented video to generate a completely original and realistic video from scratch. And I think we're going to see this happening in the video game industry really fast, and also in simulation for training machine learning models, where we essentially just generate the geometry that we need and then fill in with a realistic looking environment afterwards. Video completion, which allows us to digitally remove moving objects from videos, which in the most recent versions, even that smoke cloud would have the gap of the car filled in. So this is improving pretty fast. Shadows are all taken care of now in the latest models. We've got video face transfer, which allows us to create synthetic videos of people speaking. And note, once again, neither of those two people exist. They're completely synthetic. Video pose transfer, which allows us to create synthetic videos of people's movements, and that person on the far end doesn't exist either. And video lip syncing, which allows us to apply lip movements from one audio track to another video track, like this. And keep in mind that those 4 videos on the end are completely synthetic as well.
To help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs.
So you can see why it's so important that the general public needs to be aware of where we're currently at with these technologies, because if something like that is used for nefarious purposes, that could be pretty difficult and destabilizing for trust. All right, so as we can see, there are a variety of modern AI tools now available to developers for working with video, and these include both tools for video analysis as well as video synthesis. So now we're going to completely change gears, and we're going to learn how to build AI tools for modular AI applications, or use these AI tools to build modular AI applications. So all the tools that we've covered so far cover relatively simple and isolated problems of perception and cognition. These standalone models might be able to add new AI features to an existing product or service. However, many real-world applications entail more complex solutions than just a simple mapping from one type of data to another. So in these numerous cases, we need to combine multiple AI models together to create a full AI application. For example, an app that detects both the tone of our emails and our spelling and grammar, or an app that listens to voice commands and then provides voice responses, or an app that both identifies a person's face and the actions that those persons are doing, or the action that the person is doing. As we've seen several times now, modern data-driven AI is essentially just a function. We're just training a model that can map some kind of input to some kind of output. We saw how we can apply this general pattern to analyze tables, text, audio, images, and video, but we also saw how we can use the same pattern to synthesize new tables, text, audio, images, and video. But that's just the beginning of the types of problems that we can apply this general pattern to. There's a multitude of other types of sensors and actuators that exist in our world. In addition, just like mathematical functions, we can combine and compose these models together as well. We can combine the output of multiple models together to make more powerful predictions. And this allows us to make predictions that were not possible using a single type of input data, or to improve the accuracy of predictions by fusing together multiple overlapping sensory inputs. For example, we could combine both image and audio from a web camera for user recognition. Using both a person's visual appearance as well as their voice together allows us to more accurately identify the user. We can also chain together multiple models so that the output from one model becomes the input for another model. And this allows us to apply AI to multiple layers of data operating at various levels of abstraction. For example, we can chain object detection together with image classification to perform object classification. So the object detector locates the objects within the image, and then next we crop the images within each of those bounding boxes, and then the image classifier is going to classify the type of object within each of these cropped images. So many real-world AI applications combine and chain these various models together to form like an AI pipeline. We take some complex high-dimensional data as input, and then we reduce it to a single action, decision, or some kind of unit of data as its output. You can think of it a lot like building AI systems with Lego bricks. You can mix and match these various AI models together based on the inputs that you have and the outputs that you need. But unfortunately, most of these AI models don't just magically snap together, so we typically have to glue these Lego bricks together with a bunch of code in between. Interestingly, there's a way that we can avoid needing any of these Lego blocks or the code to glue them together. We can build what's called an end-to-end AI application. So with the modular AI that we just discussed, we're wiring together a bunch of small, highly specialized machine learning models together to solve a specific problem. But with the end-to-end AI applications, we're essentially training a single giant model or larger machine learning model to perform all of the same tasks all at once. Now, there are various pros and cons to each of these approaches to creating AI applications. Modular AI systems are easier to create, maintain, and debug. However, they require domain expertise and lots of code to wire the modules together. Whereas these end-to-end AI applications are more efficient, more powerful, and less biased. However, they're much harder to create, they require much more data to train, and unfortunately, they're not transparent as all. It's really difficult to see what's happening in the middle of one of these end-to-end AI applications. So my general advice is to always start with a modular AI application first. Start by decomposing the problem into its constituent subproblems, then solve each of these smaller subproblems with a specifically focused machine learning model, and then finally, you wire these various models together to create that full solution. Once you've solved the problem using the modular approach, though, you can actually use the modular approach to help you to upgrade to an end-to-end AI system later. However, you'll now have the benefit of using this modular application to help you train, verify, and debug that end-to-end application. And this can be a really powerful 1-2 combo for solving these complex AI problems. However, unfortunately, going into end-to-end applications is just a bit too far outside of the scope of this presentation. But as we can see, modular and end-to-end AI applications provide very powerful tools to modern artificial intelligence developers to solve complex problems in our world. All right, so finally, we're gonna just kind of take a preview of how we can build AI or use these various AI tools in order to build cyber-physical systems, things like robots and self-driving cars. So everything we've seen so far is essentially involved using an AI tool inside of an software application. However, there are many real-world problems that we want to solve that exist within the physical world. In order to do so, to solve these problems, we need cyber-physical systems, which are machines where the hardware and the software is deeply intertwined. A cyber-physical system is essentially a machine that can sense the world around it and then choose actions to achieve a goal of some kind. For example, a robot vacuum cleaner that vacuums your floors, collaborative robots, also known as cobots, that work alongside humans, and self-driving cars that drive you to your destination while avoiding obstacles. So these cyber-physical systems combine a variety of sensors to sense the world around them. In addition, they include a variety of actuators to physically act upon the world around them. Essentially, the sensors and the actuators are the inputs and outputs of this cyber-physical system function. And once again, we can conceptualize this cyber-physical system as a function. The system receives sensory data as its input, and then it produces an action of some kind as its output. However, with cyber-physical systems, this function is a bit more complex than the previous AI functions that we've seen. So we're going to walk through the iterative function here so you can get a better understanding of what this looks like. But please keep in mind that this is a vast oversimplification for the sake of time. I'm just kind of previewing so you can see how all of this fits together and how somebody would actually go about building like a self-driving car. So first, we have the current state of the environment. This is the state of the world that the system currently exists within. Next, we sense the world using a series of sensors. The sensors convert the state of the world into digital data. These data can either be audio, images, or video, like we've previously seen, or they can include data from other types of sensors like velocity, radar, GPS, and more. Then we apply perceptual machine learning models to the sensor data. These models, like we've already seen, convert the sensor data into features. Features are abstract representations of the physical world. We merge the sensor data together in a process called sensor fusion, and we represent these various features in what's called feature space. You can think of it like the system's mental model of the world that it exists within. Next, we use a planning engine to develop a plan of action, and the planning engine is often a combination of explicit programming, constrained optimization, and a type of machine learning called reinforcement learning. So with reinforcement learning, we provide reward signals for actions that lead the cyber-physical system closer to its goal, and punishment signals, which are negative rewards, for actions that lead it further away from its goal. And now using these rewards and punishments for behavioral reinforcement, the system learns to choose actions that maximize the expected likelihood of achieving its goal. Actions represent everything that the system can possibly do. For example, accelerate, brake, turn left, or turn right. The chosen action is the one that maximizes that expected likelihood of achieving the system's goals subject to a series of constraints, which the constraints are typically hard-coded. And then finally, the chosen action is fed to the actuators. Actuators include the motors and other outputs that can physically affect the state of the world around the system. And these actuators then are essentially physically acting upon the world with that appropriately chosen action. However, the changed state of the world with each action also becomes input for the next iteration of this iterative function. So we typically have to repeat this loop several times a second, choosing new actions with each iteration. And this feedback loop makes things way more complicated than the simple input-output mappings that we saw earlier. So to make things even more complicated, the system's primary goal is often composed of multiple sub-goals that must be achieved first in order to complete the final goal. And these sub-goals and the final goal are often subject to various conflicting constraints. So as we can see, CyberPhysical Systems are a very powerful tool that now exists, probably not for the average AI developer, but exists in this space for developers. And essentially, this is the future of artificial intelligence, the future of business, and likely the future of our world. And it's coming pretty fast. All right, so let's wrap things up and learn where to go next for more information. So first, I recommend that you watch my online course, the AI Developers Toolkit. If you found this useful, that presentation or that course is going to go much deeper into these topics, and it provides all of the code demos for all of the different types of things you've seen here in Microsoft, Google, and Amazon with both client SDKs and pure REST APIs. In addition, I recommend that you learn more. There's a lot that you should really be studying in data science, artificial intelligence, and machine learning that kind of paint the entire ecosystem around these new AI tools. If anyone is interested in free access to Pluralsight, just let me know. I can get you a free 30-day trial. Shoot me an email or come and talk to me afterwards, and we'll get you hooked up so that you can start learning these things. And third, I recommend that you practice. Like, learning about these concepts is one thing. Being able to do this stuff in the real world is a very different thing. So if you want simple demos, cloud APIs to play around with, or models and code repos, these are where I would recommend going first in order to start practicing with this stuff to play around. And then feel free to check out my website. I've got tons of articles, videos, and content on this topic and many more surrounding it. And finally, to quickly summarize, today we learned about the most popular modern data-driven AI tools that exist for AI developers, or developers in general. We learned about AI for tables, AI for text, AI for audio, AI for images, AI for video, building modular AI applications, and then finally, AI for cyber-physical systems. So there are tremendous opportunities for those who are interested in getting started with artificial intelligence and investing in the future of AI. It's easier now than ever to start using these tools. I highly recommend you start playing around with them, get used to it, and get comfortable in this space. If you're a software developer or an IT professional, like, the time to get started is now. So what are you waiting for? Start developing your AI skills today. All right, we've got about 6 minutes or 7 minutes for questions. So does anyone have any questions that they'd like to ask, either about this content or kind of the wider space about AI as well, too? I know a lot of people are interested in knowing how this is going to affect jobs and labor markets and ethics and stuff like that. I'm well-versed in discussing any of these topics or answering any of these questions. Yes?
I'm curious to hear more about how training works. I mean, at a very
Mm-hmm.
level. Like, you often hear that the big tech companies have access to the most data and therefore they can train the best models. But surely having a lot of data isn't enough. You would need, like, if you wanted to train a classification model, you'd need both input data and correct classification data. So what are the techniques that these companies are using to sort of, because vacuuming up a lot of data is relatively possible, relatively straightforward, but it seems like getting good feedback that you could feed into the model so that it can actually learn something from that data would be very tricky in most cases.
Yeah, there are a lot of different ways I could go with this answer. I mean, in some cases, we're using synthetic data in order to augment when we need data that we don't have. So say, for example, you're training an image classifier. Every image you've got of a Coke can or like a Pepsi can, you can move that around and change the lighting and essentially make modifications to it in order to create a much larger data set than just that one single image that you have. In addition, in some cases, if we're doing like industrial processes, we can actually use the CAD models and photorealistic ray tracing in order to create images of that object at every angle and every lighting condition and every scale. And so feeding those into the system can help it a lot. But even more powerful than having that synthetic data is self-supervised learning, which is a pre-training that we do for like deep neural networks, where we find something structural in an image. Like say, for example, you've got an image, you just remove this little square, and then you ask the algorithm, hey, what should go in there? And as it progressively gets better at figuring out how to predict missing pixels in the image, that's training the foundational layer of the network. So it's learning geometric primitives, what lines are, what curves are, and stuff like that, so that when you're finally ready to have it detect your company's logo in an image, it's essentially learned all of that stuff from this much more simple, easy to, you don't have to have a human say what the color of each pixel is because you already know the answer. So essentially using that self-supervised learning process helps you tremendously to get this to scale up without a whole lot of data. And that's why using transfer learning with like your company's logo is so powerful, because this model's already been trained with all of these geometric primitives and stuff like that, so that when you get to detecting your model, you just give it like 5 examples of what your logo looks like, and it can detect it in any image now. Beyond that, though, I think probably the most important thing to take away is that I always recommend to my clients to use the simplest tool that can possibly work. So if a simple decision tree classifier, which takes a lot less data in order to induce a decent decision tree, would work, use that. Don't use a deep neural network if a simple decision tree classifier is going to work, or Bayesian neural network, or logistic regression, or some much more simple form, for a couple reasons. Typically, it requires less training data in order to get good results, and it's significantly more transparent, so that when you're trying to debug, like, well, why did it make this decision with this customer and rejecting their loan? You can actually walk your way through that decision tree and understand, oh, it's because we've got some kind of bias with a variable that, well, I'm trying to think of a good example. There's a lot of different examples, but you could tease out why exactly you're having problems. Whereas with a deep neural network, which would just be overkill in this situation, you might get, squeeze out another fraction of a % of accuracy or so, but at what cost? And that's why this is all an engineering discipline. You're looking at one goal you want to optimize, and then subject to a series of other constraints. Once you try to optimize multiple goals at the same time, that's usually when you get yourself in trouble. So staying within those constraints and trying to optimize one thing, which it's that balance between a trade-off between simplicity and accuracy, or whatever metric you're using to optimize your model. So hopefully that helps. Yes?
What fail-safes are being put in place, if any, for the nefarious side of synthetic voice and video? Like the world, unfortunately, you got people just sucking in stupid videos.
Yep.
And believing what they see, and they're gullible enough to just say, ex-president said so-and-so, and obviously he didn't.
Yeah.
What, as far as policing that space, or helping the public, not just be duped, what is...
Yeah, so I think there's kind of 3 answers to this. Number one, there are technical ways you can determine when images are being synthesized. And so we have experts that are essentially developing countermeasures to all of these new technologies as they exist. Second is the education of the general public in terms of, yes, this is possible, and you have to trust the experts when they say that this was fake versus this wasn't fake. I think we can also develop technological solutions that may involve like the blockchain, where I could imagine in the future, anytime you take a digital photo or a digital video, it's being recorded on the blockchain that this is the original hash of this video or this image, and any modification, any software that modifies that original image is saying what sequence of steps was modified, and that's being written to the blockchain as well. So you can go back and say, this is the original image, this was a digitally manipulated image, they did this to it, cut out this part of the video, and so you'll have this kind of chain of auditability of any digital media at some point in time in the future. And then the last thing I think I should mention, though, is that, and I don't mean to sound disrespectful in saying this, but as a general public, we've been duped by misinformation for generations. This new level of sophistication is just another iteration in the digital editing of photographs, the cutting of videos to tell a different story than what's actually happened. So we've been manipulating, analog and digital media for millennia, and people always seem to fall for it. But once again, this is why I think the more dangerous thing is the lack of trust in experts now, because they're going to be the only ones that will be able to tell us, yes, the blockchain said this is the original image, and here's how it was modified. And if we don't believe the experts, we're going to be in trouble trying to figure out what is true and what's not anymore. About another minute if anyone's got a question. Short question? Or a really long question that we can take out in the hallway afterwards? Okay, well in that case, we'll wrap things up here. If you do have any questions, just chat with me out in the hall afterwards and we'll keep the conversation going. All right, thank you very much.